Welcome to another edition of The Tutor Wizard. I'm your host, Tim. That's my avatar. Our elder cat is Callie, so she's your maître d' today, your hostess today. Callie's got to be about 12 or 13, I think, by now. Very interesting kitty cat. What we're doing today is Introduction to Statistics, lecture number 12, following hot on the heels of number 11. Hey, hi, Logarithmic. You haven't heard from anybody yet. I'm just chatting. I've got a typo here in the, or not a typo. I have an interaction in the chat. Logarithmic, I will follow up on that and see what's going on. Give me a couple. Well, let me do this. Let me do this stream first, and then I'll be in touch with the lads and see what's going on. Anyway, lecture 12 today. We are going to continue on with confidence intervals now for the two-sample proportion problem type. Oh, okay. Thank you, Logarithmic. And we're also going to segue into hypothesis testing for one sample proportion as well. And I'm thinking tomorrow what we'll do is the two-sample hypothesis test and chi-square. That's the tentative idea anyway. As with all things Twitch, subject to change. Based around what? The whims of the host, I suppose. Gotta find some more cats too. We've seen the 4 cats that live here. Adrian has kitty cats, and I have pictures of those, so I'm probably going to be popping them up as well. And eventually we'll get Lorenzo's cat on here as well. So more cats than we know what to do with. Anyway, today's got to be kind of a quick one, because things need doing. And, well, I need to be doing them, as the saying goes. We had a bit of a burst of weird weather here last evening. It's very unusual when Environment Canada gives you the alert on your phone to be aware of the sudden appearance of life-threatening winds. That's a new one on me, but they were forecasting a rather severe thunderstorm cell moving through the area with gusting winds up to 130 kilometers an hour, which here in the center of the North American continent is kind of unusual. Kinda? That's very. I've not seen that before, and I'm old. The gusts that did go through the region where I live weren't that bad, but yeah, I could see where flying debris could knock you down and keep you down if you were unfortunate. Okay, let's carry on. Boom. Next slide. Let's look at the formula for the two-sample proportion confidence interval. Now, what's going on here? Let me get my pen ready to go here. So remember, we're trying to determine if there is a significant difference between two measured proportions. So we're going to go p hat 1 minus p hat 2. It's not vital, unless you're told specifically which one you subtract from which, because it's the difference that matters. I tend to always subtract the small one from the large one, simply to remove a negative sign. And that works for me, but unless you're told specifically to do it a certain way, it really don't matter. Then we need a critical number in Z. I'm going to talk about that here in a moment. That's why the T table is up on the screen. You're saying T, but this is Z. I'll show you in a minute. Trust me. And then we need the standard error, which is this rascal right here. And this is simply the variance, the standard deviation of p hat for the first sample, and the standard deviation of p hat for the second sample. That's really all that is. The most important thing is to remember when you're working with confidence intervals, you're using the statistic and not the parameter here. That's why these are all the hat symbols. Now, let's take a look at this table. Let me move this screen around a little bit. Now, you can get all these critical numbers from the Z table if you wish, but for the programs that I'm working with, the coursework, You can find these at the bottom of your t-table. You see, the thing is with the t-table, degrees of freedom, I'm looking at right here, the degrees of freedom make reference to the sample size. And as the sample size increases, the difference between the t distribution and the z distribution vanishes. You'll notice in all these columns, all the numbers, let's look at the center column here. Numbers start very large, and as the degrees of freedom increase, they approach a value. We say they converge. And for 95%, right here, they converge to 1.96. The 1.96 can be found on the Z table, which makes sense since t converges to z. As the sample size increases, these numbers on the infinity row should be the same values you can get from the z table. Now, some of them have 3 decimals. That's because they're calculated mathematically as opposed to a table lookup, but these are the numbers we're going to use. So one of the things I always tell people to do then is when you have your t-table printed out, or if you want to edit on a PDF, just mark the infinity row as your z critical value. So that's where you're going to get these from. And of course, the t-table will be used extensively when we move into working with mean values, of course. Now, we can find these values, like I said, on the infinity row here. These are the same values on the z table. Not a big deal. We'll talk about that as we move on. I've got a couple of examples set up today where we'll take a look at some of these tables. Okay, let's move on here a little bit. I've got a problem ready to go. And we have, in a city, we'll call it City A, 45% of 20 people agreed with a certain question. In City B, just down the road, 48% of a sample of 45 people also agreed with the same question. We're going to construct a 90% confidence interval to determine if there exists evidence the cities have different agreement rates. Yeah, pretty straightforward. Let's carry on. Now, we have our formula here that we're going to use at the top. And I like to have the difference between the two proportions with a positive sign. So I'm going to go City B minus City A. And that is not a big deal. That's just how I choose to do it. So we're going to go P hat of City B minus P hat of City A. Now, 90% confidence. Let's take a look at that number. We need a critical value for that. So here's the 90% right here. And since this is proportions, we're going to use 1.645. That's our multiplier. Let's put that into our formula. Here we have 1.645. Now, am I going to be able to wedge that big square root in here? Probably. Let's try. Now, just so you can follow along with what I'm doing, let's move that formula up here a little bit. So I've got to do the square root symbol now. So for City A, or pardon me, City B, 48% are in favor. So remember when you're working with percentages, you got to convert them to decimals, so just move that around. So 0.48, now 1 minus that is 0.52. So we're going to do that. And that was from a sample size of 45 people. All right, there we go. And for City A, we had 45%, so 0.45 times 1 minus that, which is 0.55. That was from a sample of 20 people. All right, we're good to go there. Now, what's the difference between A and B? Well, here's 48, here's 45. The difference then is 0.03. We're going to have plus and minus 1.645, and if you're working along at home, I will work out the square root separately instead of just writing it up and throwing it out there. Now, my trusty Texas Instruments calculator. I'm a TI guy, been one for years. It just seems to be the one that naturally makes sense to myself. I got 0.48 times 0.52. And divide that by 45. And that'll be 0.55. I'm going to carry all the decimals, so I'm not going to write that down on the screen. I will put the computed square root up. And then we're going to have 0.45 times 0.55 divided by 20. And that gives us 0.012375, yada, yada, yada. Now let's add those two numbers together. And remember to take the square root. So our square root then works out to 0.1339. So recall from our previous chat that this is called the margin of error, which we have to add and subtract to our estimated difference between the two proportions. So let's multiply now by 1.645, and we get this. So here's our 03, and our margin of error is a very large 2202 percentage points. That's a very large margin of error, but not a surprisingly large one because the sample sizes are very small comparative. So there's not a surprise there. Now we need to turn this, of course, into an interval. So we got to go 0.03 minus that, which should give us 0.19. Now, is that going to be 1998 or what? I better do this. Just let's make sure. Minus 0.2202, and it is 1902. Okay, just had to make sure. Sometimes I forget to carry the 1, or borrow in this case. And then if we add that, we get 0.25. Oh, I screwed up. This could have a negative sign on it. Well, I was looking at that and I'm going, that can't be right. I'll tell you why it couldn't be right in just a moment. 2502. So there's our 90% interval. 90% confidence. The reason that didn't make sense without the negative sign is if I had left it positive, I would have had just the two numbers, both of which a difference of 3 percentage points. That doesn't make any sense at all. So it's the old sniff test thing. You train yourself eventually to notice that these numbers don't make sense in context of the problem, and then it becomes, well, what did you do wrong? Oh, you forgot the negative sign. Anyway, so how do we interpret this? So remember from a previous lecture that here in the center is the estimate. And here it's the estimate of the difference of City B and City A's agreement rates. Well, if two things are the same, statistically or in reality, then we're saying the difference has to be 0 or very close to 0. And if two things are different, then we're either going to be our interval will either be entirely greater than 0 or entirely less than 0. But you'll notice here the lower bound is negative and the upper bound is positive. So by the intermediate value theorem from your study of calculus, 0 lies in the interval. And since 0 is in the interval, this is how our conclusion is made for us, that there is no significant difference between the two cities' agreement rates. So how do we summarize that? We can say, since 0 is in the interval, there is no significant, I should start typing this stuff, I guess, no significant difference. I like handwriting. Between A and B. So that's how you'd answer that if it was a hypothesis-oriented question. And that's kind of what it is. If we were just talking about the confidence interval, we would say that the measured difference between City A and City B is 3 percentage points with a margin of error of 22.02 percentage points, giving a lower bound of 0.19 and an upper bound of 0.25 with 90% confidence. So, do it either way. Depends on what the question's asking you to do. Okay, now I've cooked up something here in the next slide. This one's a bit unusual. I've never actually seen anybody be asked to do this, certainly not with a two-sample test. But you know what? A little math never hurt anybody. So that's what we're going to do here. So for the previous problem, we're going to do some reverse engineering and find the critical number and corresponding confidence level associated with a significant difference. Now recall what I just said. A significant difference then would have 0 outside the lower bound, upper bound interval. So how are we going to work that out? Well, let's think about this for a minute. That means the margin of error has to be smaller than the difference between the two proportions. So that means we need ME, margin of error, has to be less than 0.03. Now, what is the margin of error? Let's go back to the previous slide. We don't have to do all the work. Now we know, let's look here. We know the square root worked out to this. The thing that's going to change is this. Let's go back over here, 1339. So that means we need 0.1339 times some critical number to be less than or equal to 0.03. Don't worry about the inequality here. You could put an equal sign there, and long as the left-hand side is smaller than the right-hand side, you're in business. So let's take a look. I should do a series of lectures on how to handle inequalities. Everybody struggles with those. I think they're not taught extensively, at least in the schools where most of my students come from. So we're going to divide this out. So what is this business equal to? Let's find out. I'll grab my calculator here. Now, 0.03 divided by 0.1339. I guess it helps to turn the thing on. I'm waiting here. No, but it's not doing anything. 0.03 divided by 0.1339, and I get 22. I worked this out earlier, and that's not what I got. Oh, I know why. I bet I know why. Wait a minute. We used 1.645 on that. Okay, well, let's see. I made a boo-boo again. How about that? So the margin of error has to be less than that. Well, let's just carry this on. We'll troubleshoot our way through this. It's not the first time I've screwed this stuff up. Let's just go back to that previous look here at this. So we had the square root of this, the square root of that. Square rooting it gives us 0.1339. And yeah, that looks about right. Okay, well, let's keep on keeping on. So this worked out to 2240. All right, so that suggests, now it'll be, remember that's a critical number, so this could be plus or minus. Now, let's see what confidence level that's associated with. So remember, this is a critical number. So let's go over here. That's why there's a Z table sitting here. So here, let's look at negative 0.22. So here's negative 2, 0, 2, 1, 2, 2. Oh, there we go. 4129. Now, what does that tell us? Well, this is where we've got to be careful about these kind of things. What that tells us, remember, confidence intervals, if this is negative 0.22 and this is positive, remember these are crits, right? 2, 2, then the 4129 is suggesting that this is 0.4129, and that means this one up here is 4129. I don't like this. I think I made a mistake, but you know what? If I did, I'll correct it tomorrow. Anyway, if we add these two numbers together, we get 8258. Well, okay. So 0.8258, we got to go 1 minus. Remember, we still need this thing in the middle to get our confidence level. And this is going to be 0.1742. Don't need a calculator for that. So 17%? I'm not too sure I like that. I think I've made a mistake here. I really do. But you know what? If that's the case, we'll just correct it on lecture 13. So say when I worked this out before, it actually worked out to 0.071. And that made far more sense than this. So it makes me wonder if I've made a mistake on that. Let me double check that. Quick computation. It's entirely possible that I messed that up. Now, I was going to multiply that by 1.645, wouldn't I? Yeah, that doesn't really matter. We need to be less than 3 percentage points. Okay. Yeah. Okay, so we had this times this. And back over here for a minute. All right, so margin of error was this thing times the critical number, had to be less than that. And this divided by that, yeah, no, that seems right, but let's check one more time. Because it should almost work out some way to put the, I wonder if it's like the TI's got a video out. I wonder if I can integrate this into the stream. So I have to play with that. I do have a cable around here somewhere. We'll give that a whirl sometime. I think that'd be kind of interesting. This is a TI Inspire CAS. This is the CX model. So if anybody knows, I wouldn't mind knowing about that. So we had 0.45 times 0.55. Let's go back here. I'm just going to redo the numbers to make sure I didn't totally pooch this. It's entirely possible, you know. Okay, so we had 45.55 divided by 20. And then we're going to go plus 0.48 times 0.52 divided by 45. And we get that, yeah, 1339. That's the same number. And, yeah, 0.03. divided by last answer is 2204. Okay, well, that's fine. I'll follow up on that tomorrow if there's a mistake. Otherwise, we'll leave it. The point is, you have to use your tools to work things backwards. And that means doing what we've done here. Whether the outcome or not is should be in agreement with what I did previously. So I'd like to work this stuff out before I go online, or not. The method is the same. We knew the margin of error. So what I'm getting at with the margin of error having to be smaller than the difference, remember, I need, whoops, that's not ready to draw. Let's move this around a little bit. Let me illustrate why we need that to be smaller than the margin of error. So if the margin of error, let's make a number line. Zoom, okay, we've got a lower bound and an upper bound. Now if I mark this as the measured difference of 0.03, and I have to be smaller than that, that means I need to be, let's see here, I need the measured difference, 0.03, minus, oh, this is going to be greater than, okay, so I'll say minus 0.29, and then over here I'm going to have 0.03 plus 0. Oops, hang on. Getting kind of silly with that one. 0.029, and then over here we're going to have 0.029. Let's get this out of here because I got this on the wrong side. There we go. Boom. Over here, the measured difference is 0.03. Boom. Now, that means this works out to 0.01 and an upper bound of 0.059. So with this in mind, now the interval is entirely greater than the measured difference. If I had it the other way around, so I had a negative, it would have been the same thing. The point is I've now excluded excluding 0. And that means we do have a significant difference. Significant difference exists. So that's how you can work one of these things backwards, provided you don't make an arithmetic mistake, of course. So that's what the goal was. So that means a margin of error of 0.29. Just work this one more time. 0.29. I'm just pulling that. That's got to be equal to 1.645. Well, no, I need a new critical number for that. Dum-dum. Do 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 is equal to, boom, 0.03 divided by our, oh, there we go, standard error times, I know what I did there, okay, all right, and just checking the calculator again. Nah, we'll leave that for now. Anyway, I will follow up on this bad boy tomorrow, and we'll go from there. But anyway, I got stuff here I want to cover off. Let's move on to next page. Come on. Now we want to. So this is another example of something we did on the previous stream, where you have a uncommon. That guy right there, an uncommon percentage. So 88% is not sitting at the bottom of the t table, so now we have to use the z table to get the critical number for that. So I wanted to redo this. Otherwise, it's still a two-proportion confidence interval. So let's get that out of the way first. Okay, let's understand what it is we're hunting for. So confidence intervals deal with the center. So if this is 88%, 0.88, we have 12% unaccounted for, which means I need 0.06 here and 0.06 here. So here's just an excerpt from the Z table. We're going to go inside to find a value as close to 6 percentage points as we can. And you'll notice that that is spanning these two numbers. That's 0.606, which is too big by 6/10,000ths, and 0.0594, which is too small by the same amount. So the value we want is right in the middle. So I've truncated the table just for space. So this is our second digit. This is 0. This is 1. This is 2, 3, 4, 5, and 6. So between those two columns then must be 5.5. Now what's the first? Well, I guess I shouldn't. Yeah, we'll leave that for now. So we come back over here. So we're using z is equal to, z star is equal to negative 1.5, and we want that. Hang on, I screwed that up. Didn't circle that big enough. Boom. So this is 0.055, because remember these are 0.1, 2, etc., etc. So we have this. This will be our critical value for this question. Everything else will be the same up here. So let's go P1 minus P2. Oh, but we don't have P hats. Remember from previous that P hat is computed by success condition divided by the sample size. So this is 0.33. And that'll be A, and this will be B. Now here we have 20 out of 45. So that should be 0.44. And of course these are both decimals that continue forever, and we're not going to chase that around. We're just going to use the two decimals because we're interested in the method. So I'm going to leave it alone with A minus B here just to show you the negative stuff, okay? So we're going to have A is 0.33 minus 0.44 plus and minus our critical number, which is 1.555. And then we need this. Big square root. So we got 0.33 times 0.67 divided by 36. And then over here, I got that little blip in the way. Let's get rid of that. Then we have 0.44 times 0.56. And this is divided by 45. Now, what do we have over here? This is negative 11 percentage points. So let's mark that in there. And then we have 1.555. And calculator work. What do we have? Let's see what we got. 0.33 times 0.67 divided by 36. And then we're going to go plus 0.44 times 0.56 divided by 45. And the result is 0.1079. I'm going to round that. That's rounded from 78. There we go. Now, this is our margin of error, which we need next. Let's get that. 0.1078. I rounded that. And then 1.555. Margin of error is 1676. And this is negative 0.11. There we go. Let's see what we get. So again, we could answer questions by saying that the measured difference between sample A and sample B when we subtract B from A is negative 11 percentage points. In other words, sample B is 11 percentage points smaller than sample A. We have a margin of error of 16.76 percentage points, and we are 88% confident with our estimated difference. We could answer that way if we wished, but we can also make the interval, and that's what we're going to do. So here is negative 0.11 minus 0.1676. We get negative 0.2776. And then we add the same. And we get 0.0576. So again, you'll notice we have one positive number and one negative number. And in the same way as we concluded previously, since 0 is in the interval, 0 in the interval means there is no significant difference. In other words, we would fail to reject a null hypothesis if that was the question. Fail to reject H null. Now, just as a quick reminder, what would H null be if this was a hypothesis test question? Well, H null would have been that the population proportion for sample A minus the population proportion for sample B is equal to 0. And I didn't really specify either way the alternative hypothesis because it doesn't matter, since 0, the hypothesized value, is in the interval. This has to be interpreted as a fail to reject. Recall that when we talk about confidence intervals, the values between the lower bound and the upper bound are equally plausible as the true value of the unknown parameter. And the unknown parameters that we're concerning here is what's the difference between P null A and P null B. So no significant difference is our conclusion. Rushback99, hi, how are you? Got a new person on the chat. Rushback99, You play football? 'Cause that's kind of a football username, seems to me. Actually, if you're playing college ball, it's kind of cool, actually, because for the local university, up and for the last number of years, I didn't do it last semester, because I picked up some different work and there were some changes in the academic program as well. Hopefully, I'll be back with them. No, just chilling and study for exams. Right on, nothing wrong with that. That's the whole point of this, is to hopefully provide little help for exams. But I have spent many years teaching mathematics, well, statistics, calculus mostly, some linear algebra to the University of Alberta Golden Bears football team. And that was great fun because yeah, they're a good bunch of kids and you can joke around with them. The problem is now half the time I make some silly ass cultural reference and then I have to explain it because, it's I've aged out. But that's half the fun anyway. Anyway, um, athletics at the university level is quite good times. Only starting university in September. Cool. Any particular program, Rushback 99, that you're looking at? Or just hoping to find your way forward? You've got an ad running. Yeah, perfect time for a chat. I'm going to flip ahead here to the next page. There we go. Ooh, electrical and computer engineering. Okay, props to you. Hey, we're back. Just in a chat conversation with Rushback 99 on the chat. It says starting university in the fall and electrical and computer engineering program. And I've got to give you credit, man. That's going to be you're going to have a lot of math. But there's nothing wrong with that because it's really interesting math. But you're definitely going to be looking at linear algebra. You're definitely going to look at, well, depends how hardcore you want to go, but you've got a couple of semesters of calculus in there. And statistics is always handy. Mean time before failure is a very important topic. I can't say I have insider knowledge to this, but the way I have it figured out, so when you go into, you better enjoy it. When you go into a electronics shop and they offer to sell you, let's say you bought a $500 monitor, and they offer to sell you the extended warranty for $50. And I think to myself, now, wait a damn minute. How does that really work? Now, let's assume that there's no profit motive built into that. That's just a flat 50. That means if there's no profit motive, the $50 is 10% of the price you paid for the monitor. So we're simplifying this all to heck, but the point I take away from that is, oh, you're expecting it over a course of 2 years, a 10% failure record? And specifically, let's think about this a little bit more. So the manufacturer will have a warranty for the first year. Okay, so whatever dies then. But if the store is trying to sell you a extended warranty for the end of year one through the end of year two, and it's 10% of the replacement cost, and that says to me, at the very minimum, they're expecting a 10% failure rate. And then you have to ask yourself, what the hell am I buying here? Because if it's got a hypothesized 10% failure rate, somebody's done the math in the background. They know what the mean time before failure is on their product. Because any engineer worth their salt should be able to compute that. So you may want to find yourself a different monitor, is my point. See, math is useful. You don't let anybody pull shenanigans on you in the consumer world. If that extra warranty is a significant cost, a significant percentage of the cost of a replacement unit, then that thing's got a expected high failure rate. Okay, enough of that. New slide here. We have sample proportion hypothesis test. There's the formula we're going to be using. Remember with these formulas, the general layout is always the same. Let's look at the top here. Let's look at the numerator. P hat's the thing that you measured. You're going to compare it to some expected values, some population values. So in other words, it's the difference between what you measured and what you were expecting to get divided by the uncertainty or the standard deviation, or standard error is what we're going to call it now. The thing to keep in mind, though, this is slightly different from what we were doing with the confidence intervals. That this is not p hat down there. That is now p null, the population value. Now, keep that in mind. If it goes wrong, you may have put the wrong p in there. Just a quick question, Rushbag99. Are you a European student, North America student, in the Pacific Coast student? Roughly geographically, approximately, where are you at? And I haven't forgot about the Southern Hemisphere either. I'm just, go. Ah, Swiss. Cool. So Central Europe. There's, I'm trying to think of the, what's the big tech school? I can't recall the name of it off the top of my head because I'm trying really hard to think of the name of the big tech school, and I'm not coming up with it. No matter. ETH, thank you. There we go. There we go. Now I'm using some soft. If I'm not mistaken, let's take a look at Open Boards. Let's look at Open Board here for a minute, because I believe this is a Swiss project. About. Come on, give me that. Okay, why aren't you going there? There we go. Yeah, here we go. Geneva, Switzerland, openboard.ch. Yeah, this is an excellent piece of software. It's a fork from Open Sancore, or Sancora, which stopped development in 2013. But the Swiss, as you see here, have kept it going. So look at that. There you go. Look at that. So isn't that... this is actually an excellent piece of software. It's not entirely bug-free. The software, for what you see on the screen 90 times out of 100, is bug-free. But if we look in here, there's a whole bunch of applets, applications that can use. So here's a protractor. We have triangles. The compass is so useful. And I can even do LaTeX with this, with the apps that are built in here. So I have the LaTeX to SVG, which allows for vector graphics. I would just drag this over like so, he said confidently, waiting for it to work. Come on, hurry up and load. I'm asking a lot from my this is a fairly old laptop, so it's a bit slow. So if I go in here like so, and I type e to the 2 pi, boom, like so. Whoops, I missed the I. Darn it. E to the 2 I pi. Boom. There we go. So there's e to the 2I pi equals 1. And then I can click here, and I can drag this over to the canvas, and then I can close this, and there. That's really kind of cool. You're doing some vector calculations. Cool. Actually, keep an eye on our stream schedule. There's 3 of us running this show. Lorenzo, who's currently sitting in a help center somewhere right now helping students this afternoon. It's afternoon here where I'm at. Is doing some linear algebra vector instruction, probably fairly basic. You might be beyond that right now. And then we have Adrian, our PhD holding mathematician. If you look at the Tutor Wizard on YouTube, you'll see several years of archived videos that Adrian has done. And you may find a lot of what he does is very interesting. He has a PhD in applied math, so it's not full of theoretical computations. It's, hi, here's how to do it, which is kind of the process, what's not the word process, it's kind of the the philosophy that I follow. My thoughts are, if you're taking a math course, your professor is going to give you the theoretical, you're going to get what you're paying for. But if you're having trouble, you want to understand this stuff, statistics or calculus. I do a little linear algebra too. Um, it doesn't make sense for me to repeat verbatim what you saw in class. I'm going to try to put it in simpler or different terms, certainly different terms, maybe even simpler, to help you understand what's going on. So it's what I do here, what we do here would be an adjunct to that. Look at me babbling on here. I should get back to doing this stuff. Okay. Anyway, so one sample proportion hypothesis test. This is the formula we're going to use. Now, let's take a look at the hypotheses for this. The null hypothesis will always be that the population proportion is equal to some value. And the alternative will be that the population proportion is either not equal to that value, less than that value, or greater than that value. One of those three choices. Just to remind everybody who's just catching up now or need a little reminder, whenever you have the does not equals for the alternative hypothesis, this brings you to the two-tail test. Because we're not prejudging if something's bigger or smaller, we're suggesting it might be different. So when I say two-tail test, we're saying that rejection regions can either be the lower tail or the upper tail. Now there's two ways to handle this. One way, the first way to handle this, is to go, when you finally compute the p-value, 2 times the p-value versus the level of significance. The second way to do this is to start off by taking the level of significance and dividing it by 2, and then compare that to the standard p-value. Doesn't matter which way you do it, just do one of the two, don't do both. There's also a method to do this with critical numbers. We'll talk about that in another lecture. Let's move on. I've got a couple of examples ready to go here. So here we have an important referendum. And this referendum, for it to pass, 2/3 or 66%. Now I've said 66. I know you may say, well, that should be rounded. Well, we're going to specifically say 2/3. So humor me. I want it to be 66%. And what do we have? We have results in favor of the referendum, 625, 375 people oppose it. At the 1% level of significance, is this evidence in favor of the referendum? Well, let's find out. Here's our formula that we're going to use, just like before, but let's write the hypotheses first. H null will be set at 0.66. And we're going to set the alternative then. We want to know, is this sufficient to pass? It's in favor of the referendum. So we're not going to do a two-tail test here. This is going to be greater than 0.66. And alpha will be 1%. There we go. Now, let's compute. Here is our test statistic Z. Oh, what do we got here? Doing calculation for phase shifts for electromagnetic devices. That's Rushback with vectors. Oh, you know what? I would strongly suggest you take a look at some of the material that Adrian has on our YouTube site, because a lot of the stuff he does is things like this. I'm not entirely sure of his full catalog on there, because there's a lot of material. But have a look on that, unless that's assuming you need help. It sounds to me like you're pretty competent, so we won't worry too much about that. Okay, I could probably sit here and chat all day, but I really should finish this problem. All right, so we don't have any p hats, right? We don't know what p hat is. Well, here we have to figure things out. So we got 625 said yes, but how many people were asked? Well, there's 625 plus 375. It's no coincidence that worked out to 1,000, by the way, because that's what I did. And that makes this an easy 625 is our p hat value. So we have 0.625 minus 0.66. And for square root, we got 0.66 times 0.34 divided by 1,000. And we'll put that under a square root. So the numerator is, so this is 660. So that should be negative 0. What? Why am I having trouble with you? 0.35. Oh, math. Arithmetic. Sometimes it's hard. Not as hard as vectors, though. No, that's not true. Vectors are just different. They're not terribly hard. They're just different. Yeah, so we got the numerator, right? Now let's take a look at that denominator. So we got 0.66 times 0.34 divided by 1,000. And that gives us a 0.01. Wow, that's just going to round all to heck. 150. Okay, so that's a rounded value. All right. Whoops. Shouldn't have done that. Trying again, Tim. Come on. D-pad on my calculator is getting a little sketchy, so sometimes it sticks. Now, how did that work out? Okay, negative 0.35 divided by, and we get a z-score. This z-score is equal to 2, and remember the z-table only uses 2 decimals, so I had to round this to 34, which isn't what I thought it was going to be, unfortunately. That's why I've got the wrong portion of the z-table sitting there. Don't forget the negative sign. Now, I'm going to have to go and fish that, so let me just get rid of this, as this is the wrong one. Boom. Let's get rid of that, and I'm going to flip over here to my textbook. And we want the 2.34, almost, right? There we go. So this is another, here is good old open board in action. So I'm going to highlight this, and then I can copy it in case you hadn't wondered, if you haven't figured it out by now. This is running on a Linux install, OpenSUSE, or SUSE if you're in North America. So again, for Rushback 99, a European, one of the older ones too, by the way, version. Okay, how come I'm not getting a paste here? Trying again. Control V. Ah, there it is. Okay, let's grab that. All right. Now, there's our Z table. Negative 2.34. So here is, whoops, get back over there. All right, so we're on row negative 2.3. So this is second decimals up here, so this is the 0, 1, 2, 3. Here's column 4. So that means our p-value is that value right there. So the p-value, our p-value, now you're saying, wait a minute, why are you going that way? Well, here, let's write this down so I don't forget. P-value is 0.0096, but alpha is 0.01. Whoops. And what do we have? We have this is less than. Not by much, but it is less than. It's very close. Now, we would reject the null hypothesis, and we do have some evidence in favor of the referendum, but man, that's pretty close. Almost as close as the late 70s. There was a referendum in Canada about Quebec's separation. because Quebec's francophone province. It's got its own culture. Historically, when um, General Wolfe defeated Montcalm on the Plains of Abraham, that's when the British took over the French possessions in Canada, in Upper and Lower Canada, back in the well, that would have been what's I don't remember the exact date, 17 something something, I guess it was. The British, to keep the peace, didn't try to assimilate the French holdings, so Quebec, into Anglo culture, and Quebec has, prospered as a French enclave here in North America. And for the longest time, there was a fairly strong referendum or separatist movement. But the point I'm getting at is the referendum was in favor of remaining in Canada by the slimmest of margins. And this example here, coincidentally, is in favor of a referendum here by the slimmest of margins. Anyway, yeah, math and history together again, like peanut butter and chocolate. Let's take a look at the next page. I think I got something else here. That's right. We want to construct the 99% confidence interval for the previous question. So oftentimes it's useful to compare results like this. So let's see what we get. Now, this one is really close, so let's see what the difference is. So we had a difference of 0. No, there's no difference here. We had a measurement of 625. Okay. Now, plus and minus. Now, the 99% confidence. Recall when we were talking about the t-table and the infinity row. Hey, what's going on here? How come that didn't work? Well, anyway, we're looking at... why are you acting up? Let me move that around a little bit. I don't know why oh, let's move that over here. This is 2 parts, so I had to pull the table apart to make it fit. There we go. Now, let's take a look at this one. So here is our okay, I can't doodle on you. Why can't I doodle on you? I doodle up here? No, that don't matter. Anyway, here's 99%, and that means we need 2.576 as our multiplier. Let's put that in. Now remember, confidence intervals uses the p-hat value, so we have 0.625 times 0.375, and there were 1,000 people in this referendum. And now we're going to have to work that out. So I'm just going to do those calculations all in one fell swoop. Archback 99 says he used to struggle so much with vectors. Now I enjoy it after spending countless hours. Yeah, well, that's the only way to learn math is to do it. And I fully admit that in times I have been quite lazy with that. Most of what I do is undergrad math and usually 1 and 200 level courses, because almost all my work is with students who are just trying to pass the course. I very rarely work with someone who's a B plus trying to get into the A zone. I'm working with students all the time who are just trying to turn a fail into a pass, and if they can turn it into a C or a B, then that's just gravy, but as long as they don't fail. Although one of the more interesting things I've done over the years is I've taught university math to students who are blind, can't see. And if you think about the amount of visual instruction that goes on in mathematics, that's a big challenge. But so far, it's been very enjoyable, and I have a record of students passing. But it's made me a better math person in that I have to think about what I'm talking about much more carefully. Okay, so we got to turn this into an interval. So we have 0.625 minus the margin of error, which is 0.5856. I'm going to round that. Then we have to, of course, add that as well to get the upper bound. And we get 6644. So at the 99% confidence level, we got a very, very slim pass. So, but we also have a fail. No, I'm sorry, I messed that up. This is not a pass, this is a fail. So we know that p hat is in here. P hat is 0.625, 62.5%. But remember, the H null value is that P null is equal to 0.66. Whoops, it's hiding under that. I'll get that out of the way. There we go. There it is. This is in here as well. So recall when both the expected value and the calculated value lie inside the interval, we fail to reject. H null. Boom. There we go. Okay, and what do we got left here? I think that's it for today. Yeah, I have no more slides. Cool. Now I'm going to ask you to be patient with me in that I'm going to try to see if there's any other, let's get back here to page 1. If there are any other math people online. This is one of our 4 cats here at CASA, CASA Tutor Wizard. Well, actually at my place, at Tim's Tutor Wizard place. This is Callie. I will be featuring some of the good girls from Adrian's place coming up here pretty soon too. So it's cats and math. Now what I want you to do is just be patient with me. I'm going to try to see what's available for raiding. Let's go over here. Is there any math channels that I can raid? Let's see what we got. Okay. Okay, so let's see what's going on here. Raid channel. If there happens to be someone online doing math right now, we'll raid them. And if there are not, well, then we'll just wrap it up and call it done for the day. Filtered by category. Math. That's a good category. Do, 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 do. Boom. Let's try that one. Do we have anybody online? We do not. Oh, wait a minute. I am not on camera. Math fan Brian. Should we rate him? Why not? Let's do that. I don't think there's anything going on there. I don't see anybody. End testing. Okay, I'm not sure what's going on with that. Okay, let's back up. Let's see if we can go to a different filter. So that was math. But let's see if we can find, I know there was a math is fun. Let's try that. Math Magician, that's my handle. Nobody there either. Well, I must be doing this the wrong time of the day. Let's try one more time here. How about? Math is horrible? You know, math is horror. No, we don't like that. We don't want to do that. Mathica, Math Blaster, Pre-Algebra. No, I think that would be kind of boring. Math Challenge, Mathematic Adventures. And I think we're kind of stuck today. Well, you know what? That's fine. Not a problem. Now let's try Math Magician. Nope, not there either. Okay, you know what that means? That means we're going to wrap it up today. Now, I do want to conclude this discussion on inferential statistics for proportions really soon. So I'm thinking another about 24 hours from now, sometime around noon local time, 1 o'clock local time tomorrow, I'll do lecture 13. We'll finish off the business of two sample proportion hypothesis testing, and then we're going to talk about how you do multiple comparisons, same data type, which will be chi-square. So that's the plan, if all goes well. And in the meantime, thank you everybody for joining me today. Rushback 99, nice to chat with you in Switzerland. And everybody else who was on our chat here as well today. Logarithmic was here earlier. Thank you for popping in again. And yeah, that's about all I have for you today. Let's leave it there. And I'm going to slide over here and end the stream. And thank you for joining us. We'll see you soon. Bye bye.